We saw that a very useful and versatile way of looking at surfaces is by parameterizing them from an external coordinate system UV. There is some region D in the UV plane, and there is a function that maps it into the 3D. If we write UV as functions x UV of I plus yuv of j plus z uv of k. We saw, for instance, that at a given point on the surface, we can easily find the tangent plane, because the normal to tangent plane is this magical vector ru cross rv, where ru means the vector that is partials of the coordinates with respect to u, and partial v is just the analogous vector with partials with respect this time to v. And part of the assumptions, a good parameterization, an admissible one, would be where these are non-zero and non-parallel, so that this cross product is non-zero. Okay, so it's interesting and geometrically nice to have something for the tangent plane, but it's not that much of a useful object anyway. A more useful object is that of surface area, and for many reasons, from engineering for instance, you may wonder, or you may want to know, how much material is needed to build something of a certain shape. The book again goes with Riemann sums and some hand-waving arguments why this is the case and should be the case and stuff. There is a lot of linear algebra, not just from R2 to R2, but R2 into R3. There is deep change of variables stuff happening, if I want to be honest with you. So a proof of this really is beyond this course, and that's why we just go ahead and say, to find the surface area of this S, you want to integrate a very special quantity over the back here in region D. And that quantity is, fortunately, the familiar Ru cross Rv, but we want a scalar value, so the absolute value of that will be the right quantity. So that is a theorem in mathematics, and as I said, the proof is quite involved and deep. One thing here that is a part of the claim, a bold statement that is being made here, is that this integral will be same value independent of a parameterization, because notice that parameterizations are extrinsic objects. You get to choose your parameterization. If you ask someone else, they may come up with a totally different way of parameterizing the same surface, a totally different D. Maybe for them they are more clever and they parameterize from a complete box, and they have their own R, and now they compute their quantity here, their respective integral, and if these were not the same, then these two people would have a fight over what should be the surface area of our object, and it would be stupid to define the surface area of the object in a way that depends on who and how we parameterize the surface. Fortunately, this is not the case, and this integral is indeed an intrinsic object. The key here is inclusion of this. So, of course, if we don't include this, we just put 1 here. That means surface, that will be area of D. And of course, area of D cannot be equal to area of S, because you can just do a different parameterization where you just resize D into half its size. So this quantity will play a big role later on, and together here you can think of this as some intrinsic quantity, that if you integrate something against this, it does not depend on parameterization, and that will be topic of next section. But here to finish, we want to do this special case of having a surface given by some function f of x and y, because that is one of the common cases and easy cases where you don't have to really go to a secondary into a secondary coordinate system. You don't need a UV coordinate system. You have your surface and it's parameterized over its shadow. So if I follow my coloring of parameterization area with green and the actual object of interest, the surface, in blue. So the object, the surface, is the set of points with f of xy, where xy is chosen from the shadow D. In this case, if we want to find the, so we have previously we claimed that the area is equal to integrating over the shadow this quantity, 1 plus partial of x to power 2 partial of y to power 2 dA, which is the shadow, let's say dx dy. Now here we can also say, here in new viewpoint, we can say that take the function r from xy to be x, y, and f of xy. You can check that for every xy in the domain D, this point belongs to the surface. It's exactly the point whose projection down below is xy. Okay? And here I'm thinking of xy playing two roles. So there is this separate place here in the coordinate system here. There's a copy of the region D, right? And this is the R map, which parameterizes my surface. So my u and v are just x and y. So we could have switched the names, but why do so? So x, y, just be aware that here are playing two roles, but in such a compatible way that there is no room for confusion. Okay, if I follow this parameterization, so with this parameterization, we must have that area of our surface S is equal to partial with respect to x, cross product partial with respect to y, dx dy. So do these formulas give us the same thing? Do these formulas give the same value? I mean, they must. If they don't, we are in big trouble. One of them has to be incorrect. The answer is yes. Why? Let's look at Rx. So here, let me calculate in red so that we know what's happening. So Rx, partials with respect to x. So you just take partials of these coordinates one at a time. So this becomes f of x. Ry becomes 0, 1, f of y. If you cross product the two, I believe you get minus f of, do I want to go with x first? Yes. Minus f of y, and then 1. I believe this will be the 1. And now once I take the norm, so the yes part is yes, because the norm of Rx cross Ry is exactly 1 plus f of x to the power 2 plus f of y to the power 2. So you see that the two formulas are reconciled. They both, in fact, give the same quantity. So this is the formula if you have the surface given as a function, graph of a function of two variables. And this is the more general formula for any parameterization.